So electromagnetic wave, the wave direction, the direction of electric and magnetic field are related, and E cross B is direction of the wave direction, and C is related again B as C as E by B. Okay.
Okay, sir.
Transformer. See, this is one coil, and this is the second coil, and a passing current in this coil I. So because of this, a magnetic field will be produced, right? Current in the solenoid will produce a magnetic field. So this magnetic field will link this second coil. Okay, this is magnetic field lines. Okay, and if this I is a function of time, then this B is also a function of time. And this, since this B is function of time, the flux linking this coil phi will become a function of time. And now if I use Faraday's law, EMF is d by dt of phi. Okay, so once I have this, I have a induced EMF across this terminals. Okay, so this is basically a transformer. Here we have one coil which will pass the current, and here in this another coil we get the voltage. Okay, and this so this is in air. Then the magnetic field is coming out of this coil. Will go in all directions. Okay, the magnetic field lines will go everywhere. Okay, but suppose if we put a soft iron core, which is there in a transformer, this soft iron core is a conductor of a magnetic field. Okay, then the 99% of this magnetic field lines will come inside. Okay. So here on the input side, we have a current and a corresponding voltage, say V1 and I1. And we have the current at the secondary side as V2, and the corresponding current is I2. Okay, and this V1 or the current I1. So this V1, say I1, R1, this is a coil. Okay, so this V1 will produce a flux, right? That is proportional to I1. So it will be dependent on I1, and this flux produced is proportional to this number of turns here, right? Suppose this has got 5 turns, the flux will be produced with something. Suppose if you make this number of turns as 10, then the flux will double. So it will depend on the number of turns of this coil 1. N1, I1. Okay, and then this is a transformer. Here are 2 coils. One is a primary coil, another is secondary. Okay, so EMF induced in the secondary, P5 by T, the primary is P5 by T. Okay, so there is a flux which is passing in this circuit. Let the flux be 5. Because that flux and this voltage across this primary coil are related like this. Okay, energy d5 by dt. This is Faraday's law of electromagnetic induction. Similarly, the flux in this coil, this secondary voltage is related as this one, energy d5 by dt. And since the flux is same, we have ES by NS equal to EP by NP. The flux is same, right? The flux linking this one, and then this one is same. The flux per unit. Okay, so from this I get ES by NS equal to EP by NP. Okay, so I can either increase or decrease the voltage. Actually, you can remember, so V1 by number of turns in the first coil equal to V2 by number of turns in the second coil. Okay, so if V1 is input, then V2 is output. So N2 divided by N1 into V1. So if number of turns in the secondary coil is more than the number from the first coil, this implies that V2 is more than V1. So this is a step-up transformer. I'm assuming one has input, okay, and 2 is the output voltage. So output voltage is more than the input voltage if number of turns in the second coil is more than the first coil. So this is a step-up transformer. So similarly, if N2 is less than N1, there will be a step-down transformer. Okay. So the job of a transformer is to either increase the voltage or decrease the voltage. And since power is not lost, the input power is V into I on the primary side, and the output power is V into I in the output side. There is the secondary coil. So IPVP equal to ISVS. We are assuming there is no power loss. So the input power should equal the output power because there is no loss of energy. That's the assumption. There are no losses. So in that case, the power is same on the input side and the output side. So if you use this, I'll get, so the relation between VP by VS is IS by IP. So VS by VP is IP by IS, which is NS by NP. So if the voltage is going up in a step-up transformer, the current is going down. Suppose NS is more than NP by 5 times, then the secondary voltage is more than the primary voltage by 5 times. It's a step-up transformer, but the current will go down by 5 times. So that the product of the current and the voltage is same. Got it? Okay, in a step-up transformer, the voltage is going up, but the current will go down. So that the product of the current and the voltage is same. Because we cannot create the power. Whatever is the power, it should remain same on the input and output side. So if voltage is going up, means the current should go down. So it's energy conserved in a transformer. In the sense, like if you assume it's an ideal transformer where there is no losses, then the energy is conserved. Whatever is the input energy or the input power is same with the output power. That's why if the voltage is going up, the current will go down, so that the product of the current and the voltage is constant or same. Okay, so energy is conserved from the ideal transformer. Is it clear? Yes.
Sir.
Okay. Maxwell equations, you know, right? 4 equations are there. And what is its basis? Where do you get that from?
Ampere circuit law.
Maxwell equation basically relates the electric field, magnetic field, and there will be some time variation of it. Okay, so the first one is Gauss law of electrostatics, which is what is that thing? Integral E dot ds, which is the flux, this is the surface integral over a closed surface equal to Qn by epsilon naught, right? This is the first equation, Maxwell equation. It gives the electric field, it relates the electric field to its source, which is the charge. Second equation is Gauss law for magnetic field, B dot ds over a closed surface. What is this thing equal to? Anyone? Gauss law for magnetic field, this is 0. Because the charge inside a closed surface in case of magnetic field is always 0. See, this is a closed surface. In the case of electric field, I can have positive charge is here inside it, plus Q, and outside I can have minus Q, and here also some minus Q2, Q1. So the net charge is present inside Qn. This can be positive or negative. Okay, but in the case of magnetic field, I cannot have positive or negative charges. It's always magnetic dipole, right? North pole and south pole. Some bigger north pole and south pole. So in this case, if we take the net magnetic charge inside, it's always 0 because north pole and south pole will cancel. So the net magnetic charge inside a closed surface is always 0. What do we call it? Magnetic charge equal to electric charge. Understood? See, if this Qn is inside, if the Qn is, suppose I force a current, I have this source of charge as only dipoles, say minus Q plus Q combination. I only give this as the electric charge. Then everything inside will be in form of dipoles, say minus Q and plus Q. minus Q1 plus Q2. In that case, the net charge present inside is 0, right?
Yes, sir.
Okay. But in case of electric charges, I can have separate plus charge and minus charge. So I can keep plus charge inside here, Q3, and I can place minus Q3 outside. In that case, the net charge present in this closed surface is plus Q3. Okay. In the case of magnetic,
என்னது சார் திருப்பி சொல்லுங்க சார் புரியல சார்
see, in case of electric field or electric charge, I can have positive charge and negative charge separately. I can have a plus 5 coulombs independently of minus 5 coulombs, irrespective of whether it's there or not. Okay, so in that case, I can put plus 5 coulombs inside and minus 5 coulombs outside. Okay, in that case, the net charge present inside this closed surface is plus 5 coulombs, right?
எஸ் சார்
Okay, but in case of magnetic field, I don't have magnetic charge. I only have this combination north and south. Okay,
ஓகே
I
சார்
break this, I'll get a smaller north and south. Okay, so if I'm able to keep only north here and south outside, then I can say the net magnetic charge present inside is 1 north. Okay,
ஓகே சார்
this sort of splitting is not allowed, no, in magnetism. I cannot separate north and south pole. See, the electric dipole plus Q minus Q, I can separate them.
எஸ் சார்
Okay, I can separate it to infinity. I can, but for magnetic field, if you take a bar magnet, north pole and south pole, if you try to break it, I'll get two smaller north pole and south pole. I cannot separate north and south
ஓகே சார்
separately. So
எஸ் சார்
whatever
எஸ் சார்
source of magnetic field is present will be in form of pairs. It cannot be monopole. It is not possible that I have a south pole inside and corresponding north pole outside. This is not possible. Okay, so whatever magnetic charge is present will all be in terms of pairs, and this pair combination is 0. Like plus Q minus Q, net charge is 0.
ஓகே சார் அண்டர்ஸ்டுட் சார்
So the net magnetic charge inside a closed surface is 0. So that's why integral B dot ds of a closed surface, which is equal to a Gauss law in the electrostatics, is 0. So this is second Maxwell's equation. This is first Maxwell equation, which is Gauss law for electrostatics. Okay, integral E dot B is Q epsilon. This is in first chapter. Okay, and integral B dot dA for the corresponding magnetism. This is 0 because this Q is actually in, right, inside charge. The corresponding magnetic charge which is inside the surface is always 0 because they come in pairs. I cannot separate north and south. But in electric field, electric charge, I can separate plus Q and minus Q. And I can keep plus Q inside and minus Q outside. In that case, Q in is plus Q. Or I can keep minus Q inside and plus Q outside. In that case, Q in is minus negative charge. Negative charge. But in case of magnetic, I cannot separate north and south. Either both should be inside or both should be outside. When both are inside, the net is 0. Like north is like a positive charge and south is like a negative charge. So the net combination is 0. It's always 0. Okay, so this is Gauss law for
Sir.
magnets.
Sir,
What?
what if both are outside, sir?
Both are out means 0, right? Nothing is there inside.
So Gauss law will be 0, sir, for inside and outside.
See, let me do it for electric this thing. Suppose I have minus 5 coulomb plus 5 coulomb outside. What is the net charge inside here? 0, right?
It will be 0, sir. Yes, sir.
Suppose if I have minus coulomb here and plus 5 coulomb here, what is the net charge here? Inside?
0. Same.
0. But if I have minus 5 inside and plus 5 outside, okay, then the net charge is minus 5.
Minus.
Okay, so
Okay,
this sort of
okay.
separating minus charge and plus charge is possible in electric charges.
Yes, sir.
Understood.
Okay, but in magnetic charges, the source is, say, we can take it as a bar magnet, it will be north and south. If we try to break this, it will become too small, north and south. So either this whole thing should be inside or whole thing should be outside. I cannot make, this is not a north and south, so I cannot keep a dipole like this. If it is a dipole, I cannot keep minus Q here plus Q here. If you consider this dipole, either the whole thing should be inside or whole thing should be outside. Okay, so
Okay, sir.
So that's what is the information in this second equation. This is called Gauss law for magnetism. This is indicative of the fact that there are no magnetic monopoles. Okay, electric monopole is electric charge, positive and negative. But in magnetism, there are no monopoles. The minimum is a dipole, which is north and south combination. And the third law is Faraday's law. Induced EMF is d phi by dt, and the induced EMF over a closed surface, d phi by dt. So this entire is okay. Induced EMF is so the third Maxwell equation is induced EMF is d phi by dt. Okay, and this is nothing but voltage. Okay, and voltage and electric field related as gradient, right? d by dr. So v is integral e dot dr. Okay, this line integral along a contour. That's what is here. Integral e dot dl. This is the voltage, which is d phi by dt. This is Faraday's law of electromagnetic induction. This E is electric field. This E is EMF, which is same as V. Okay, and V and E are related by this. This is in first chapter. Negative gradient of the potential of the electric field. So from this I get the voltage as integral E dot dl or dr, whatever. Over a line integral. This is over a contour. This is over a surface, because that you can figure out from here. This is dA, right? This means the indication is over a surface. This element is dl. It's integral over a line element. And this closed path is a closed path. This closed one is a closed surface. This is a closed surface. This is a closed path. This also here also the equation is dl. This is Ampere's circular law. This first term, mu naught IC, and Maxwell contribution is this second term. That's why it's called Maxwell law, Ampere-Maxwell law. So you can have magnetic field without the current, but with the changing electric field. This is called displacement current. This second term. This IC is conduction current, which is the current passing through a copper wire or any wire. And this is the current. There is no actually conduction current. It's because of changing electric field. Between two capacitor plates, when the charge in the capacitor plate is changing, electric field is changing. So that is equivalent to a current. That current is displacement current. So these are the four set of equations which form the Maxwell's equations. First one is Gauss law for electricity. Second one is equivalent to a magnetism. And the zero is because there is non-existent magnetic monopoles. Third one is Faraday's law. Fourth one is Ampere's law with Maxwell's contribution. Maxwell's contribution is the second term, which is called the displacement current. Here you can have magnetic field without the conduction current, but because of changing the electric field. Okay, so these are the four set of equations which form them. So the solution of these equations are these wave equations, electromagnetic waves. E not equal to whatever. So if you put E, this as a function of those set of four equations, it will solve them. Okay, and this solution has got a particular property that if it is sign this one, same function should be here also. And E should be X means B is Y, then the direction of function is Z. Maxwell basis and waveform given waveform. Okay, this is one last concept. Suppose I say for electromagnetic wave, E is E naught, let me say 5 volt per meter into sine omega, I say 3t minus omega t minus k is there, right? Let it be 5 and make 6. 6z. Okay, so this is a, let me call it dx. So this is a wave traveling in the z direction. So this is a sine wave, right? Okay, and it's traveling the z direction. So it's a function of both time and space, which is z. Time variation is here, and the space variation, which is z variation, is here. Okay, so what is wavelength of this wave? This wave has got a wavelength, it has got a frequency, and something is called a wave number. I'll define. So what is the wavelength of this wave and what is the frequency of this wave? This is being given. The form of the Ex is given. So from that I can find the Wavelength of the wave. So what is wavelength? Wavelength is periodicity, right? And it is space period. You know what is period, no? Whatever is repeating. Here, what is repeating is this part from here to here. Is going to repeat, right? Suppose this is Z, no? So suppose this is, say, 5 meters, then the wavelength is 5. Okay. But here in this case, you have to find out what is that wavelength. It need not be 5, it can be different from 5. How do you find that? So if I replace Z by Z plus lambda, okay, then this value should be same, right? So 6 into Z should be same as 6 into Z plus lambda. Same, or I can say equivalent. That means that 6 into lambda should be 2 pi. See, whatever is sine, if I change this quantity by whatever is the previous one plus 2 pi, will the value of this thing change? Sine theta is same as sine theta plus 2 pi, right? Understood? Sine of 30 degrees is same as sine of 30 plus 360 degrees. Is it correct? Someone?
Sir.
Karthikeyan asked me. Karthikeyan, understood or not? Sine theta is same as sine of theta plus 2 pi. Even cos theta is same as cos of theta plus 2 pi. Just a minute. See, this is theta degrees or theta radians. Okay. For this particular thing, whatever I calculate, sine, cos, or tan, it is same as if you go one complete revolution come to this point, right? For this thing, this angle is 2 pi plus theta. So sine of theta is same as sine of theta plus 2 pi. Because sine theta and theta plus 2 pi are the same point. I'm just completing one circle and come to the same point. Okay. Similarly, cos of theta is same as cos of theta plus 2 pi. Similarly, tan theta is same as tan of theta plus 2 pi.
Yes, sir.
Okay. Understood. All trigonometric functions, sine, cos, tan. If I change the argument by 2 pi, the value will not change. That you should know. Okay. So here in this case, when changing Z by Z plus lambda, the value should not, that is the meaning of the wavelength, right? Periodicity. So whatever is extra coming, that is 6 lambda, that should be equivalent to 2 pi. Only that the value is not changing. When I change Z by Z plus lambda, the value Ex should not change. That means this argument should not change. That means that the 6 lambda, which is coming as extra, should be equal to 2 pi. Then it will not be changed. That means lambda is corresponding to the period. So 6 lambda equal to pi, 2 pi. From there, we get the wavelength lambda as 2 pi by 6. So for this particular variation of Ex, okay, from this I'll get the lambda as 2 pi by 6 meters. Similarly, I can find the frequency nu. Frequency nu is time period. Someone is asking something in chat. Okay. Anyone has some question? Okay.
Can you
So
repeat the
similarly,
lambda part, sir?
Just repeat the
Lambda.
question. Lambda?
Yes, sir. How 2 pi is equals to 6 lambda?
Yeah. Okay. See, space period means, see, at this point, whatever is the value, if I go this distance by lambda, I should get the same value. Right? That's the meaning of space period. If I have this value, okay, if I, from this point, if I go by lambda distance, I should get the same value. Got it or not?
Okay, sir.
Huh?
Okay, sir.
So because lambda is the duration after which it's repeating. So when you change z by z plus lambda, since lambda is a space period, Ex should be same. If you change z by z plus lambda, Ex should be same, right? Because lambda is periodicity.
Okay, sir. See, this is sine periodic, this is the period, no, lambda. So whatever is happening here, if you go by a distance of lambda, same thing should happen. Whatever is happening, if you go by a distance of lambda, same thing should happen. Okay. So Okay, sir.
in this z, if I increase z by lambda, this value of Ex should not change. Okay. So that means if we change z by z plus lambda, if this argument value, if it changes by 2 pi, then sign of that this value will not change, right? Or I can say Ex should not change means this thing should not change. I'll just repeat. See, Ex should not change, right? That means that phi is not changing. That means this should not change when I change z to z plus lambda. Okay. So
Okay,
sign
sir.
of something will not change if this thing is changing by a factor of or by a term of 2 pi. Because sine of theta is same as sine of theta plus 2 pi. Okay.
Okay,
So when I
okay,
change
sir.
z,
Okay.
so when I change,
Understood, sir.
so when I change z by z plus lambda, the extra thing I'm getting is 6 lambda. So if this 6 lambda turns out to be 2 pi, then this value will not change. Okay, so from this I get the 6 lambda should be equal to 2 pi.
Yes, sir.
From this I get lambda is 2 pi by 6.
Understood, sir.
Okay, next is time period. Nu is time periodicity. Time period. So if we change t by okay, nu is actually time period, but actually nu is related to the time period as 1 by t. Actually, capital T is time period. Capital T is time period, and nu is related to capital T as 1 by t. Okay, so suppose I change by t by to t plus t, it will become 3 into t plus capital T, right? So this extra thing which I'm getting t, 3t, that should be equal to 2 pi, for this value not to change. That means the time period is 2 pi by 3. So from this I get the frequency as 3 by
3 by 2 pi.
okay. So given this waveform, I can able to find the wavelength and the frequency. And wavelength, this one more quantity called wave number, which is nothing but 1 by lambda. And this is basically number of wavelengths per unit length. Number of wavelengths.
So 6 by 2 pi, sir.
Hold on. Suppose this whole thing is 1 meter. Okay. And how many wavelengths are there? This is first, second, third, 4 wavelengths are there, right? So 4 lambdas are there in one. So K is 4 in this case. So, and the wavelength here, lambda is 4 wavelengths are there in 1 meter, right? So wavelength is 0.25 meters. Got it? I'll repeat it.
Yes, sir. Understood.
This is the first wavelength. This is second
Yes, sir.
wavelength.
Yes, sir.
Third and fourth. So 4 wavelengths are there in 1 meter. Okay, that means lambda is 0.25 meters. K is the wave number, which is number of wavelengths in 1 unit length or 1 meter here. So K is 4. So K is related to the wavelength as 1 by lambda. This is called wave number of wavelengths in a unit length. So K is 1 by lambda. That will be 6 by 2 pi.
Yes, sir. Okay. Here they have put 2 pi by lambda. Here 2 pi is given coming because of the, instead of saying per unit length, I can say for one complete circle. See here, k is in terms of z, no? So z is 1 by meter, and this thing, whole thing should be in radians. So instead of defining k as 1 by lambda, I can also define as 2 pi by lambda. So here the idea is it's like a circle. So in this complete circle, the angle is 2 pi. So in 2 pi radians, how many wavelengths are there? Another way to remember this one is, see, this is sine of something, right? So this thing should be in radians, right? Z is in meter, so k should be 1 by meter. So meter will cancel, and whatever is remaining should be in radians. That is 2 pi. Okay, so just accept this 2 pi factor if you don't understand. Okay, this
Okay,
k is called wave number. Okay, that's what I'm saying. Given E waveform, I can find B waveform. That's what I've done, right? I can find the direction. Okay, here I find wave number. So since suppose I'm given this Bx, I can find E, electric field correspond to the electromagnetic. First, I figured it's along the minus k cap, right? So E is along minus y. Okay, and then this function form should be same sine omega t minus this one. Okay, same thing will become here. I'll be E naught, and E naught is E naught by B is E by B is C, right? So E naught is B. So this will be B naught into C. Okay, B naught is known, so E naught is known. So once this Bx is given, I can find E minus y. Because this thing I just have to drop here. And instead of this B naught, I have to write B naught into C. Okay, so given E waveform, I can write B waveform. Here I've done the other way, given B form, I written E. Similarly, if E is given, I can find B. Same relation. Function should be same, and direction of E cross B is the direction of wave propagation. From that, I can find out. Okay, so the meeting will end in 5 minutes. So tomorrow I'll send a WhatsApp message and see your response. And if it is required, I'll have another session tomorrow at 9.
morning, sir.
No, not morning, in the night.
Okay, sir.
Tomorrow morning, I'm going
Okay.
out.
Okay.
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 Okay. So if you know all these concepts, you can solve all the questions with the test. Okay, any particular 5 minutes are there before the thing shuts
Are
down?
there derivations to this time? Are there any
Derivations.
derivations? Or only
What about working of a
problem-based?
transformer? You just have to say how the voltage is getting stepped up or stepped down
Okay, sir.
depending on the number
Step
of
down.
turns. And Vs
Yes,
into
sir.
Is is same as IP into Vp, right? That is because
Yes, sir, yes.
power is conserved. There is no energy loss.
Yes.
Ideal transformer. So that's sort of a derivation.
Sir, based on impedance, you will ask problems or derivations, sir.
So if, for example, capacitor circuit, pure capacitance, conductive voltage source, show that the power dissipated is 0. Power
For
pure
resistor, sir.
No, resistor power is dissipated. No, for pure capacitor circuit, power dissipated is 0, right? Because it's equally positive and negative. It's average of sine into cos, right?
Yes, sir.
Average
Yes,
of
sir.
sine into cos is same as average of sine to omega t, which is 0. So that derivation proving that
Okay, sir.
consumed by a pure inductor or pure capacitor is 0. That derivation.
Okay, sir.
Okay, I'll send you a message tomorrow. And depending
Okay,
on
sir.
response, I will see whether I need another
Sir.
class. Yeah.
Sir, weightage in this chapter, sir.
Main thing is which chapter?
No,
Weightage.
weightage.
Stress model.
Weightage.
Almost equal. 1/3.
Okay. Okay, sir.
Focus on the concepts I have said.
Okay, sir.
Okay, sir.
Okay, sir.
I'll just send PDF. Just a minute, just a minute. Okay, we'll close. Yeah.
Okay, sir.
Okay,
Thank
sir.
you, sir.
If anyone who has got a question, we can clear it. Otherwise, we can close.
Okay, sir. Thank you, sir.
Yeah.
Sir, no questions, sir.
Okay, okay, fine. You can leave them.
Thank you, sir.
Yeah. Good night.
Good night, sir.
Yeah.
Thank you, sir.
Thank you, sir.
Sir,
Yeah.
sir, what about impedance, sir? We will ask problems based on impedance or derivation.
No derivation.
And
No,
RLC, sir.
resonance condition that
Yes.
XC and XL should cancel, right?
Yes,
XL is
sir.
equal to
J,
XC, no, sir.
Yeah.
RS.
So that will be the condition on frequency. Omega not equal to 1 by root LC.
Yes, sir.
So in that case,
1 by root.
current is impedance is minimum, current is maximum. So power distribution in the circuit will be maximum.
So we need to derive that resonance condition, sir.
No, suppose I say when will the power be maximum? Power distribution maximum. It will be maximum at the resonance condition.
Yes, sir. Okay, understood, sir.
So power is I square into Z or V square by. It says maximum power.
Sir, what about motional EMF, sir?
Not
Lorentz
there for this
equals
current. Not there for the coming.
this, okay, sir. Okay.
Thank you, sir.
Yeah, bye.
Good night, sir. Bye, sir.
Thank you, sir.
Yeah.